We will now discuss embedding theorems. We've already seen that if omega is contained in R, say an interval, then W1p of omega is continuously embedded in C of omega bar. In fact, it is an absolutely continuous function. That is what we saw. So we'd like to generalize this, see if you have information on W1p omega in some subspace. Of course, we already have W1p of omega is contained in LP of omega. That is from the definition. Now we want to know if you have, because of the extra information we have on the derivatives, namely that the distribution derivatives are also LP functions. This is an important piece of information. Does that tell you more about the function? So in particular, we would like to know if W1p omega is contained in some space of continuous functions, differentiable functions, or so on, or at least in some other Lebesgue spaces. So LP, for instance, do you have W1p omega continuously embedded in some other LP space, some LP star where P is not equal to P star. So we want to know W1p of omega, is it embedded in LP star of omega, P not equal to P star, if such a thing is possible. So we would like to answer such questions, and so in particular we look for an inequality of the form mod u 0 p star Rn is less than or equal to C times mod u 1 p Rn for all u in W1p Rn. So this will mean that W1p Rn is continuously embedded in LP star Rn where P star is not equal to P. So first of all, we want to, we can prove such a result, and the proof may just look like magic or just manipulating P and else various P, N and all these quantities, but a simple analysis will tell you where to look and why we should look there. Okay, so let us assume such an inequality is true for all u in W1p of Rn, and let lambda greater than 0 be a positive number, okay, and fix it. So you look at the function, the scaling, okay. So if u is in W1p of Rn, so you define u lambda of x as u of lambda x, then u lambda is also in W1p of Rn. In fact, you can compute all its norms. So let us take, what is du lambda by dx at any x? This is nothing but by the chain rule you have that this is equal to lambda u lambda x, u dash, sorry, d by dxi u of lambda x. So we will now therefore integral on Rn mod du lambda by dxi power p dx is at x, okay, is equal to lambda power p, okay, lambda is positive, so lambda power p, so integral on Rn mod du by dxi at lambda x power p dx. And therefore if you now make a change of variable lambda x equal to y, then lambda power n, so lambda x equal to y, so lambda power n x equals dy dx will be dy. Remember, dx is dx1, dx2, dxn. So each time you pick up a lambda from the scaling, and therefore dy is this. So this will become nothing but lambda to the p minus n of integral over Rn mod du by dxi at y power p dy. So you have mod u lambda 1p Rn, which is the sum of all these quantities to the power 1 by p, will be equal to lambda power 1 minus n by p, because I have taken the pth root at the end, of mod u 1p Rn. Now in the same way, we can look for some other any p star. So if p star is greater than or equal to 1, you have mod u lambda 0 p star Rn. What is this? This is nothing but u of lambda x. Okay, so you are going to make lambda x equal to y. You will pick up again dx equals dy by into lambda power minus n, and then you are taking the p star root. So this will be equal to lambda power minus n by p star mod u 0 p star Rn. So now for all functions we are looking at the inequality of this form. We are looking at this inequality for all functions. So this has to be satisfied by all the functions u lambda etc. So 0 less than 1 by c should be less than or equal to mod u lambda 1 p Rn by mod u lambda 0 p star Rn. This is that inequality which we are saying is true for all functions, and that if you take into account the two previous computations here, so we just substitute, this is lambda power 1 minus n by p plus n by p star mod u 1 p Rn by mod u 0 p star Rn. So this is what we get. Now let us look at this number 1 minus n by p plus n by p star. Suppose this number is positive. Okay. Now if this number is positive, then you let lambda go to 0. So then this will go to 0. Okay, and therefore you will not be able to get this inequality. It will violate this inequality because it is bigger than or equal to 1 by c, which is strictly positive. Now if so, you let lambda go to 0, so you get a contradiction. Okay, if 1 minus n by p plus n by p star is less than 0, then you let lambda tend to infinity, then again this quantity will go to 0, and you will once more get a contradiction. Therefore, inequality possible only when 1 minus n by p plus n by p star equal to 0, that is 1 by p star equal to 1 by p minus 1 by n. So this is the defining relationship for p star. So if at all you get W1P Rn, if you want to show that it is in LP star of Rn, possible only if 1 by P star equals 1 by P minus 1 by N. And this of course implies that 1 by P star is less than 1 by P, and therefore this means P star is bigger than P. Okay, and also this has to be greater than 0, and therefore you have that P should be less than N. Okay, P should be less than N, otherwise this will not be even positive, and then P star is bigger than P, so P is greater than or equal to 1, so that is fine, and N must be bigger than P, and then you will have 1 by N, 1 by P minus 1 by N will be positive. Okay, so we will therefore restrict our attention to 3 cases. So 3 cases. P less than n, we will show that W1P Rn is contained in LP star Rn for where 1 by P star equals 1 by P minus 1 by n. Okay. If P equal to n, we will show that W1P Rn is in fact contained in LQ of Rn for all Q belonging to P up to infinity, and infinity is excluded. Okay. And if P bigger than n, you can show that W1P of Rn is contained in C of Rn. Okay. In fact, much more Helder continuous and various differentiability properties depending on how big P is and so on. So, these are the three kinds of theorems which we will use. So, we will first start with P less than n, then we will do from there deduce P equal to n, and P bigger than n will require different arguments similar to. So, in the one dimensional case you have P greater or equal to 1, and therefore you have P greater or equal to n, and therefore you had these two results. Okay, the second and third were valid. Okay, so now before you go on, we need a technical lemma due to Gagliardo. Okay, so let n be greater than or equal to 2. Let f1 fn belong to L n minus 1 Rn minus 1. So, there are n functions in Ln minus 1 Rn minus 1. Okay. Now, if x is in Rn, define for 1 less than or equal to I less than or equal to n, xi hat equals x1 xi minus 1 xi plus 1 xn. So, you are dropping the ith comma coordinate. Okay. So, we are dropping the ith coordinate. So, we put xi hat. Okay. So, this now belongs to Rn minus 1. Define f of x equals f1 of x1 hat fn of xn hat. So, we had n functions in Ln minus 1 Rn minus 1, and we are going to write like this. Then, so the conclusion of the lemma is f belongs to L1 of Rn and mod f in L1 of Rn is less than or equal to the product I equals 1 to n mod fi 0 n minus 1 Rn minus 1. Okay, because they are all in Ln minus 1 Rn minus 1, this is well defined. So, okay, so this is the lemma of Gagliardo, and which we will be using in the proof of the theorem. So, proof, let us take n equals 2. So, that means f1 f2 they belong to L1 of R. Okay, and f of x1 x2 is given by f1 of x2 f2 of x1. So, integral mod f of x1 x2 dx is nothing but, because this separates the variables. So, this is nothing but integral by Fubini's theorem mod fx f1 x2 dx2 into integral mod f2 x1 dx1, which is in fact equal to norm f1 into norm f2. Norm f1 norm of f1 mod f1 0 1 r into mod f2 0 1 r. Okay, and therefore this is mod f 0 1 r2. So, this is just separation of variables. Let us look at n equals 3. So, you have f1 f2 f3 belong to L2 of R, R2. So now let us look at integral over R mod fx dx3. I am just going to integrate with respect to the third variable. Now this is equal to, but what is f of x? F of x1, x2, x3 is f1 of x2, x3, f2 of x1, x3 and f3 of x1, x2. We are suppressing the corresponding variable. So if I do this, now we are going to integrate with respect to x3. So f3 will have nothing about x3 in it, and therefore mod f3 x1, x2 will come out. And then I have integral on R of this function which I am going to integrate with respect to x3. So I apply the Cauchy-Schwarz inequality. So that is less than or equal to integral on R mod f1 x2 x3 dx3 square power half into integral over R mod f2 x1 x3 square dx3 power half. This is Cauchy-Schwarz. Now we again integrate both sides with respect to x1, x2 and apply Cauchy-Schwarz again. So you will get integral on R3 mod f of x dx, because dx1, dx2, dx3 if I apply is therefore less than or equal to, and I have a function in x1, x2 and then I have another function in x1, x2. So if I apply Cauchy-Schwarz to this function and to this function separately, I am going to get integral mod f3 x1 x2 square dx1 dx2 with respect to R2 whole power half into integral over R2, and now I am going to square this and integrate with respect to x1, x2. Now this function has only x2 here, this function has only x3 there, so I can then split it into two integrals. So I will get, and then I have to take half again after the integration. So I will get integral on R2 mod f1 x2 x3 square dx3 dx2 this is 2 dx2, and then I have to take a power half into integral on R2 mod f2 x1 x3 square dx3 dx1, and then again I have to take a power half, and that tells you that mod f 0 1 R3 is less than or equal to product of I equals 1 to 3 mod fi 0 2 R2. Okay, and that is exactly the Gagliardo theorem. So general case, I will skip the proof, you can find it in the book, the details. So general case, induction on n, we have proved it for n equals 2, n equals 3, you assume for n and apply Helder inequality in place of the Cauchy-Schwarz which we've been applying. Okay, so this is just a technicality. So we will do. So this is the Gagliardo lemma which we will crucially use in the proof of the first theorem, namely our next theorem which we are going to prove is W1P Rn is contained in LP star Rn when P is less than n. Okay, so this is the theorem which we next have to prove, and we are going to use Gagliardo's lemma for that. Okay, we will do that next time.